Hi, good morning to all. Let us start a topic which you are a bit already aware of, and let's go in detail because when you do embedded system, it is necessary that we should know specifically what is DAC, what is ADC, and so on. You can clearly see from the diagram that there is some number in binary which is acting as an input to a DAC, and hence the output X, it's coming as an analog. So an arrangement which converts your digital input to the analog is known as digital to analog converter, or simply in a simple word we call it as a DAC. Now here we're going to talk special type of IC, which is IC based DAC. You can clearly see its number is DAC 0808, and it is very clear from the diagram itself that we have got 8 inputs and we have got a reference current exactly. So you can see this is 10 volt and this is 5k resistance. So if you divide, it comes out with 2 milliampere current. What is the whole concept in this IC is this 2 milliampere current is binary weighted based on the inputs from A0 to 8. Now for example, if all the inputs are high from A1 to 8, and high here we mean 5 volts, what I'm expecting is almost 2 milliampere current will be synced at pin number 4, and that 2 milliampere current multiplied by 5k resistance, I am expecting almost 10 volts. See, I am using the word almost 10 volts, it is never 10 volts. So what is the whole idea? This 2 milliampere current is binary weighted based on the data available here, and then it's simply with the help of op-amp, it is current getting converted into voltage. Imagine a situation that all the inputs are 0 except A8. That means the data is 1, 0, 0, 0, 0, 0, 0, 0. So what exactly the data means? There is only most significant bit. In this case, corresponding to 2 milliampere, only 1 milliampere will be synced at pin number 4, and a multiple of 5k, it gives you almost 5 volts. It's very obvious that based on the data available at a digital input, accordingly output will vary from 0 volt to 10 volt. We say it is 10, but actually it is 9.96. You will come to know the reason for it. But it's very clear that how the concept is changing. Other pins are very clear. You require 5 volt at VCC, that is pin number 13, and minus 15 at pin number 3, and whatever resistance you are connecting at pin number 14, to keep the symmetry, you have the same resistance connected pin number 14 and 15 both. And this op-amp is simply working as current to voltage converter. What the whole idea? This is a current of 2 milliampere will be binary weighted depending on the data available at the inputs. Output is nothing but a current, and hence op-amp will be converting current into voltage. Let us take very simple examples. And you can clearly see, if you see both the things here, if I0 is the current entering the op-amp, or you can say synced at pin number 4, then V0 is nothing but I0 into RF. The voltage across the op-amp is nothing but, you can clearly see, it is nothing but V0 is I0 into RF. Now if you further see the expressions here, as we have discussed here, you can clearly see the I reference, the current entering here at pin number 14 is I reference is V reference upon R reference. Let us come to the calculation very straight away. I reference is R reference is nothing but R14, and you can clearly see that I0 will be what exactly? V reference divided by R reference. That gives me actually the current. I0 will be this current. As per my calculation, this is nothing but 2 milliampere, truly speaking. You can clearly see D0 is the least significant bit, D7 is the most significant bit. If all the bits are 0 and only this bit is high, it will be nothing but 1 upon 2, and 2 milliampere divided by 2 is nothing but 1 milliampere. That is the binary weighted corresponding to when most significant bit is high. Now the further calculation you can see, corresponding output will be nothing but RF, the feedback resistance, and current. So it is very obvious formula, and we can see here the maximum current you can get is 1.99 milliamperes, because this factor, even if we add with all ones, it comes out with 255 upon 256. This difference of one least significant bit actually corresponds to current of 1.99 milliampere, and hence the corresponding output will be maximum 9.96 ampere. So you can clearly see it, since it is 8 bit, so number of steps are 8. I hope it is very clear. Then step size is what exactly? Total number of steps are 256, because this is 2:8. 2:8 gives me 256. 5 divided by 2 gives me 19.53. So each step is equal to 19.53 millivolt. That simply means when I go from 0 value to this first rise, this height is 19.53, then next is double of that, and so on. So every step. So it's very clear that instead of 8 bit, if I make it 16 bit, then the number of steps will be less. Number of steps will be more, so value of each step will be less. So these steps will be very closer. Slowly, if you rely on more bit size D2A converter, you may correspond to a straight line. That is actually the analog form. So it's basically digitized, so we get the steps. But truly speaking, it is this form. I hope you have understood it, and the remaining will continue tomorrow. Thanks for today.